let's say something about ordinary differential equations. Ordinary differential equations. So a differential equation is an equation which contains at least one differential coefficient. E.g., in part 1, dy dx plus 4y is equal to 5 cos x. Because we have a first derivative here, which is of degree 1, then the highest differential coefficient here is first derivative. So this one will be calling it first order differential equation. That is a first order differential equation. Now the second one, since we have d squared y dx squared, which contains a second derivative. So the highest order of the derivative in this equation is second order. So this we call it second order. Second order differential equation. Second order differential equation. Now the third one, the highest derivative is first derivative, but it is put to power 4. So this one will call it first order degree 4 differential equation. First order degree 4 differential equation, because it is put to power 4. After this, then we need now to tackle first order ordinary differential equations, second order ordinary differential equations. Now we are going to start from first order differential equation. First order. First order differential equation. And we are starting with the type 1. Type 1. This takes the form we are going to call this one, using the method it is being used to solve. So first order differential equation, so we will call it separable variable. Separable variable. And we say this takes the form, dy dx is equals to function of x multiplying another function of y. So dy dx will be equal to f of x g of y. F of x g of y. So in solving this, we will solve by separating the variables. A function of y should be taken where there is a dy. And now dx to join where we have function of x. Now this implies dy all over g of y will be equal to f of x dx. Will be equal to f of x dx. Now, from this, we need now to solve for y. And for us to remove the differential coefficient dy or dx, after separating the variables, we can integrate both sides with respect to the variable concerned, so that we can be able to get y as a solution. So the integral of 1 over g of y dy will be equal to the integral of f of x dx. And by doing so, we can now make y the subject, or we'll have gotten the solution of that particular differential equation. So example 1. So the dE solve the dE, dy dx is equal to sine squared x, x squared x. So in our solution, this will be dy all over sine squared x, sine squared y. Dy all over sine squared y will be equal to sec squared x dx. This implies the integral of 1 all over sine squared y dy is equals to the integral of sec squared x dx. Now, this implies also the 1 over sine squared y is cosec squared y dy, which will be equal to the integral of sec squared y, sec squared x. Now, in integrating this, the integral of cosec squared y dy will be minus cot squared will be minus cot y, which will be equal to the integral of sec squared x is equal to tan x. Now, since these were definite integrals, each side attracts a constant of integration. And now, we would like one constant added to another constant, or one constant subtracted from another constant will just be equal to a single constant. So we can include a constant of integration on our right-hand side. So we say plus a constant k. So minus cot y is equal to tan x plus k, which can also be written as tan x plus cot y is equals to a constant k. And that is the solution to that differential equation. It's equal to k, because if we take this one here and we move k to this other side, k will be minus k. But a minus k, because we still don't know the value of k, we can just presume the value is being maintained as just another constant. Hence we use what? The same k. That's how it is. That's why we are having tan x plus cot y being equals to k. So we move to example 2. So solve the d. Y dx is equal to x all over x squared minus 4 into 1 plus y squared. So this is a first order differential equation that can be solved by separating the variables. It contains the variables such a way that functions of y can be taken to where we have a dy, and functions of x can again be combined with the dx. So in our solution, this implies y all over 1 plus y squared dy should then be equal to x all over x squared minus 4 dx. After separating the variables, we can see the variable has been separated. The variables have been separated. Then we say we integrate the integral of y all over 1 plus y squared dy is equal to the integral of x all over x squared minus 4 dx. Now, here we have a quotient. We have a quotient y, quotient where we have numerator, here we have y. Denominator, here we have 1 plus y squared. What we are going to do is to check the derivative of the denominator, 1 plus y squared, is 2y. And here we have a y. So if we have a 2 up here, then we can be able to solve that integral easily. Also this one, we have x all over x squared minus 4. The derivative of x squared minus 4 is 2x. So if we have 2x here, because we can solve it easily, and adding a constant is normally allowed because there is a way you can take it away. If you multiply by a constant, then you can take it away by dividing by the same constant. That is now, we say, here we'll have 1 over 2, the integral of 2y, all over 1 plus y squared dy is equal to 1 also over 2, the integral of 2x all over x squared minus 4. Now dx. Now, if the numerator is the derivative of the denominator, when you integrate such a quotient, the answer becomes ln of the denominator, the natural log of the denominator. So we say this implies a half ln of 1 plus y squared will be equal to a half ln of x squared minus 4, x squared minus 4, plus a constant of integration, which we can call it k. Now, a constant of integration, any constant can be a natural log of another constant. Any constant can be a natural log of another constant. So we can say this implies a half ln of 1 plus y squared is equals to a half ln of x squared minus 4 plus ln of another constant, we can call it constant a. Now, we can combine this through laws of logarithm. This would be equal to ln of 1 plus y squared raised to power half is equals to ln of x squared minus 4 raised to power a half. Now multiplying a, which gives us 1 plus y squared then raised to power half will be equal to a into x squared minus 4 raised to power a half. Now from this we can remove the square roots by squaring both sides. So 1 plus y squared then will be equal to a squared into x squared minus 4. But a squared is just another constant. We can even call it b. These are just arbitrary constant because we didn't have what we call the initial conditions or the conditions given that exist for this particular differential equation. So we can now say 1 plus y squared is equals to b, where b stands in for a squared is equal to x squared minus 4. Therefore, y squared will be equal to b into x squared minus 4, this one minus 1. And that's the solution to that differential equation, where b is still arbitrary constant. Whatever we have gotten is the general solution of the differential equation given. Now, we can get the value of b if some conditions were given. For example, now, if we can be told when x is equals to so when x is equals to 3, y is equals to 10. Y is equals to, when x is equal to 3, y is equals to 2. So this implies where there is y, we insert 2. So this one will be 4 is equals to b into x squared. Our x squared will now be 9 minus 4, then minus 1. So this implies this implies 4 is equals to 5b minus 1. So b is equals to 1. B is equal to 1. Therefore, particular solution now will read y squared is equals to x squared minus 5. And that is the solution to the said differential equation when these are the boundary conditions that exist. Now we move to type 2. Homogeneous differential equation, first order differential equation, first order. Homogeneous first order D. Top of it. Stop. In our type 2 we have homogeneous first order D. We say a function of xy is said to be homogeneous if all the terms in that particular function are of the same degree. Now we have a function of xy which is this one. X squared is of degree 2. Xy, this is of degree 1, 1 plus 1 gives you 2. This is of degree 2. This is also of degree 2 because it's 2 power 2. Degree 1, degree 1, degree 1, degree 1. So all are of the same degree, a homogeneous function. X power 3, degree 3. 2 is degree 0. X power 2, degree 2. This is y power 1, degree 1. 1 plus 2, 3. So this one, degree 0. X power 1, y power 2, we get 1 plus 2, we get 3. This is y power 3. So all are of the same degree. Now, if all are of the same degree, this is a homogeneous function. This is also a homogeneous function. That is also a homogeneous function. And if we have a first order differential equation that we cannot be able to separate the variables, and within the function, we can see there is a homogeneous function, then we can solve it using the procedure of solving homogeneous first order DE. Now, the steps to be followed, or the procedure for solving a homogeneous first order differential equation, is stated as shown below. Procedure to be followed in a solution of first order homogeneous differential equation. Step 1, write the D in the form dy dx is equal to pxy all over qxy, where p over q is now homogeneous. Step 2, we now let y to be equal to v times x, where v is another function of x, which we are calling as g of x. This implies if y is equal to vx, by using product rule of differentiation, dy dx will be equal to v plus x dv dx. Step 3, you substitute for y and dy dx in equation of step 1. You substitute for y and dy dx in equation of step 1. Step 1, which is this one. Now, after that, after substituting for y and dy dx, we will now. So let's have an example on first order homogeneous differential equation. Example 1. Solve the D. Solve the D, xy dy dx is equal to x squared, y squared. So xy dy dx is equal to x squared minus y squared. Now, if we check x times y is of degree 2, x squared is of degree 2, y squared is also of degree 2. But even before we can see those terms are of the same degree. But when we see these particular terms, or these functions as they are stated here, we cannot be able to separate the variables. When we do so, it will take a long time to do it, so tedious, to enable us to separate y from x. And therefore, the next step is to check whether the equation is homogeneous. And when we check now degree 2, degree 2, degree 2, then those terms are of the same degree, and now we can now use the method of solving homogeneous differential equations. So in our solution, you can say from above dy dx and be seen explicitly that this will be equal to x squared minus y squared all over xy. From here we say let y will be equal to v times x. This implies what? dy dx is equals to v plus x dv dx. Now, when we substitute into this first equation, we say this implies what? v plus x dv dx. V plus x dv dx will be equal to x squared minus v squared x squared all over x multiplying vx. So v plus x dv dx will be equal to, as we can see, this will be x squared into 1 minus v squared all over x squared v. So this implies that v plus x dv dx will be equal to 1 minus v squared all over v. It will simplify to that. Now, we want now to separate the variables. So we can say here x dv dx will be equal to 1 minus v squared all over v minus v, which will be equal to 1 minus 2v squared all over v. X dv dx will be equal to that, which will be, this implies to now dv v all over 1 minus 2v squared dv is equal to dx all over x. We have now separated the variables. Now, after separating the variables, to solve the said dE, we need only to integrate both sides with respect to the variable concerned. So this is 1 all over, this is the integral of v all over 1 minus 2v squared dv is equal to dx all over x, which is 1 all over x dx. So the integral of that. Now this is a quotient. We can now try to see whether if we differentiate what we have in our denominator, does it gives us something that contains something in the numerator. So 1 minus 2v squared, when differentiated with respect to v, we get negative 4v. And here we have v only. What is missing is a negative 4. A constant can always be included if we like, if it is going to help us. So we say this is the integral of minus 4v there, all over 1 minus 2v squared dv. And this one we say, we remove that one, so it will be minus 1 all over 4. Minus 1 over 4, if you multiply by negative 4, you get 1, which was there before, which is 1. It's equal to the integral of 1 all over x dx. The same simplifies to minus a quarter. ln of 1 minus 2v squared, because the numerator is the derivative of the denominator, so the answer when integrated becomes ln of the denominator, natural log of the denominator, which would be equal to ln over x plus a constant k. So this simplifies now to ln of 1 minus 2v squared raised to power minus a quarter will be equal to ln. K can be ln of a. K can be ln of a. So this is ln of x plus ln of what? A. This implies what? 1 minus 2v squared raised to power minus a quarter will be equal to ln of ax. Will be equal to ax. Will be equal to ax. Now, that is the solution to our differential equation after separating the variables, but it has v in it. We would like to substitute the value of v. And before we do so, we can clear this particular bit, this power negative a quarter. So power negative a quarter, that means we can raise both sides to a power 4, power negative 4. Or this one we can write as 1 all over 1 minus 2v squared raised to power a quarter here is equals to ax. Now to clear power quarter, we raise both sides to power 4. So this one will be 1 all over 1 minus 2v squared. Then power now 1 will be equal to a power 4 x power 4. A power 4 x power 4. From here then, we can now substitute for the value of v. So this implies what? 1 all over 1 minus 2 into y squared all over x squared. Y all over x, when you square, you get y squared all over x squared is equals to a power 4 can now be written as a new constant b, x power 4. So this implies what? This gives us x squared all over x squared all over x squared minus 2y squared is equals to bx power 4. It can be simplified further as we can divide both sides by x squared. Then we remain with 1 all over x squared minus 2y squared is equals to bx squared. This implies what? Cross multiplying, we can say cross multiplying, we get x squared bx squared into x squared minus 2y squared is equals to 1. This implies x squared into x squared minus 2y squared is equals to 1 all over b. 1 all over b is just another constant. So we can say the solution x squared into x squared minus 2y squared is equals to another constant c. And that is the solution to that differential equation.